In this lesson, we're going to learn how to solve rational equations. Here's an example of a rational equation. It's called rational because it involves fractions, like you see here, and it's called a rational equation because an equation means that it contains an equal sign. We're going to come back to this exact problem later on in this lesson. To start, these are the steps we're going to follow when we're solving any rational equation. We'll go through each of these steps one by one as we solve the example problems. Before we learn how to solve a rational equation, we're going to review what we learned in Chapter 5, Section 2. In Chapter 5, Section 2, we learned to add or subtract rational expressions, like you see here. The steps that we saw on the first page only apply to rational equations, in other words, problems that have equal signs. This problem does not have an equal sign, so we don't call it a rational equation. Instead, we call it a rational expression. I want to review this type of problem so then we can compare it to the new type of problem, rational equations, where we have equal signs. So in Chapter 5, Section 2, we learned that in order to add rational expressions like you see here, step 1 is to factor the denominator and find the least common denominator. If we examine these two denominators, neither denominator can be factored. So I've put a check mark here because we've checked, but there's nothing to factor. Next, we need to find the least common denominator. We learned a trick for finding the least common denominator, and that trick is, after you've checked to see if you can factor, then just copy down the first denominator exactly as it appears, x plus 5. Then we look at the next denominator and we ask ourselves, does this factor already appear in our LCD? It does not, so we need to add it. So we're going to add the factor 3x minus 2. Now we've found our least common denominator. Next, whenever you're trying to add or subtract two fractions, you always need to get a common denominator. And that's what we do in step 2. We get a common denominator. And our common denominator is going to be the least common denominator that we found in step 1. So for step 2, I'm going to start by copying down this first fraction right here. And I'm going to add parentheses around here. You want to add parentheses whenever you have more than one term in your numerator or denominator. Now, we want this denominator to match the LCD. Let's see, we already have the factor x plus 5, but we need the factor 3x minus 2. So we're going to multiply this denominator by 3x minus 2 because now it matches the LCD. And we know with fractions, if you multiply the denominator by some quantity, you also have to multiply the numerator by that same quantity. Why are we allowed to do this? Because 3x minus 2 over 3x minus 2 is just 1. So we're really just multiplying this fraction by 1. And when you multiply by 1, you're not changing the value of your expression. Next, I'm going to bring down the plus sign, and I'll copy this fraction down here. And again, I'm going to add parentheses around the denominator since it contains more than one term. Now, we need this denominator to match the LCD. Let's see. We have the factor 3x minus 2, but this denominator is missing the factor x plus 5. So I'm going to multiply this denominator by x plus 5, and then we also have to multiply the numerator by x plus 5. Notice here, when we multiply by x plus 5 over x plus 5, we're really just multiplying by 1 again. Now, just to clean this up, I'm going to rewrite this times this, all in the numerator, and this times this in the denominator. I'm going to do the same thing over here. I'm going to write this times this in the numerator and this times this in the denominator. If you didn't want to write this as a separate step, you could have just extended this line over here and extended this line over here, and that would have given you the same expression right here. Now we have a common denominator. Whenever you're adding fractions with a common denominator, we always keep the denominator, x plus 5 times 3x minus 2, or if you switch the order of those factors, that would be fine as well. And then we add the numerators. So I'm going to take this numerator and copy it here, and then I'm going to add this numerator right here. Now remember, our goal is to get the numerator and the denominator fully factored, because then we can simplify by canceling. The denominator is fully factored, and we know that because there are no plus or minus signs outside of parentheses. So since the denominator is fully factored, leave it exactly as is. The numerator is not fully factored, and we know that because we have this plus sign outside of parentheses. If you have a plus or minus sign outside of parentheses, that means the expression is not fully factored. So we need to work on the numerator to get it in fully factored form. To do that, let's distribute here and here. 3 times 3x will give us 9x, and 3 times negative 2 will give us a negative 6. And then we'll bring down the plus, and 3 times x will give us 3x, and 3 times 5 will give us 15. Remember, the denominator is fully factored, so we want to leave it exactly as is. So I'm just going to copy down this exact denominator right here. Now, let's simplify the numerator by combining like terms. We can take 9x plus 3x to get 12x, and negative 6 plus 15 to get positive 9. And then again, I'm just going to copy down the denominator, leaving it exactly as is. Now that we've worked on the numerator and simplified it as much as possible, now we can move on to step 4, where we factor our numerator completely and then see if we can cancel. To factor the numerator, the greatest common factor would be 3. So let's factor out the greatest common factor, 3, and that will leave us with 3 times 4x plus 3. And then we're going to copy down the denominator again exactly as is. Now the numerator is fully factored and the denominator is fully factored, so we want to see if we can cancel, but there are no common factors in the numerator and the denominator, so there's nothing to cancel. So that means that this is our final answer. So this was all review. This was an example of how we add or subtract rational expressions. Now we're going to move on to how to solve rational equations. Again, you'll know that you have a rational equation because you'll have an equal sign, and you'll have rational, or in other words, fractional expressions like we see here. I wanted to review this type of problem before introducing equations because we use 2 different methods to solve these 2 types of problems, and it's very easy to mix up the methods since, as we can see here, the problems can look very similar. The only difference is that this type of problem has an equal sign and this does not. So to solve rational equations, we're going to follow the steps on the first page of this worksheet. Step 1 is the same step 1 that we saw over here. We factor the denominator and find the least common denominator. Neither of these denominators can be factored, so I've just put a check mark here. We checked, but nothing can be factored. And now we want to find the least common denominator. We can use that same trick we used over here to find the LCD. Now the remaining steps when you're solving a rational equation that has an equal sign will be very different from the steps we used when we add or subtract rational expressions that do not involve equal signs. For step 2, we're going to determine the domain. For the domain, you're asking what values of x are allowed or not allowed. Well, we know that in math, you're not allowed to have 0 in the denominator. So to figure out what values of x are not allowed, we have to determine what values of x make the denominator 0. You might be able to determine that mentally, but I'm going to write it down so we can see it here. So first we want to look at this first denominator here, x plus 5, and we want to know, when does that denominator equal 0? We can also look at this other denominator over here, 3x minus 2, and ask ourselves, when does this denominator, 3x minus 2, equal 0? And now we have 2 basic equations that we can solve. To solve this equation, I'm just going to subtract 5 from both sides, and that will leave us with x is equal to negative 5. Let's solve this equation over here by first adding 2 to leave us with 3x is equal to 2, and then we'll divide both sides by 3. And that will leave us with x is equal to 2/3. Now remember, in mathematics, we don't want the denominator to equal 0. So that means that the denominator, x plus 5, can't equal 0, which means that x can't equal negative 5. Same here, we don't want this denominator to equal 0, so that means that the quantity 3x minus 2 can't equal 0, and I'm going to put slashes through these equal signs as well. So we see that x can't equal -5 because that would make this denominator 0. And we see that x can't equal 2/3 because that would make this denominator 0. And if we want to write the domain using formal set builder notation, we start with this set builder outline, and then we insert these two forbidden x values in the blank here. X cannot equal -5, and I'm going to put a comma, x cannot equal 2/3. Now I'm going to highlight this because we're going to need to come back to this. We're going to end up solving this equation. In other words, we're going to figure out what value can we plug in for x to make this side of the equation equal to this side of the equation. If, for our final answer, we get either of these two forbidden x values, we're going to have to reject our final answer because these two x values are forbidden because they would give us 0 in the denominator. For step 3, we want to solve this equation. We could use this approach over here, where we work to get a common denominator. But with equations, there's a more efficient approach. When you're solving a rational equation, in other words, if you see an equal sign in your problem like this, I recommend you don't work to get a common denominator. Instead, we're going to use an approach that we learned in Chapter 1. In Chapter 1, we learned that whenever you're solving an equation that involves fractions, you can multiply each term by the LCD over 1, and that will completely eliminate the fractions. Let's start by copying down this expression right here, and I'm going to add parentheses around it. Now, we're going to multiply this term by the LCD over 1. So that will look like this. Next, I'm going to bring down the equal sign, and I'm going to copy this expression down here. We're also going to multiply this term by the LCD over 1. And this is allowed because with equations, you can multiply by anything you want as long as whatever you multiply the left side of the equation by, you also multiply the right side of the equation. Let's see, if we look at the left side of the equation here, we have an x plus 5 in the denominator and the numerator, so we can cancel that. So in the numerator, we're left with 3 times 3x minus 2. And in the denominator, we're just left with 1, so we don't need to write the denominator. Then let's bring down the equal sign. And over here, we have 3x minus 2 in the denominator and the numerator, so we can cancel 3x minus 2. And that leaves us with 3 times x plus 5 in the numerator. And since we're just left with 1 in the denominator, again, we don't need to write it. Now, we see that after we multiplied each term by the LCD over 1, that got rid of our fractions, and we have a much simpler equation to deal with. So to solve this equation, let's distribute the 3. That will give us 9x minus 6. And we can distribute the 3 over here to get 3x plus 15. Then to solve this equation, we want to get x on only one side of the equal sign. So I'm going to subtract this 3x from the right side and then from the left side. And that will leave us with 6x minus 6 is equal to 15. Then we want to isolate x, so I'm going to add 6 to both sides. That will leave us with 6x is equal to 21. And then I'm going to divide both sides by 6. And that will leave us with x is equal to, and 21/6 will reduce to 7/2. Now we've solved our equation. We figured out what value of x makes this side of the equation equal to this side of the equation. But before we write our final answer, we have to make sure to take a look at step 4. Step 4 is to reject any extraneous solutions. Sometimes when we're solving rational equations, we can get extraneous solutions. These are solutions that actually aren't valid. An extraneous solution would be one of these two forbidden x values. So you want to check your final answer and make sure it is not one of the two forbidden x values. This was not one of the two forbidden x values, so that means that this solution is valid. So for our final answer, we can say x is equal to 7/2. Or if you want to write your answer using solution set notation, that would look like this. Now notice, these two problems look very similar, but we used completely different approaches, and it's very easy to get these two different types of problems mixed up. to add rational expressions like you see here that don't involve equal signs, you're going to be multiplying each term by a version of 1. This is equivalent to 1 and this is equivalent to 1. We do that in order to get a common denominator. Now let's compare that to rational equations. Rational equations will again have fractions and they will also have an equal sign. That's why we call them equations. When you're solving equations, you have a lot more flexibility. You don't have to multiply by a version of 1. With equations, you can multiply the equation by any number you can possibly imagine, as long as whatever you multiply the left side of the equation by, you also multiply the right side of the equation by that same quantity, because then you'll maintain equality. So with equations, instead of multiplying by a version of 1, we decide to multiply by the LCD over 1, because whenever you multiply each term of an equation by the LCD over 1, that completely gets rid of your fractions and it makes the equation a lot easier to solve. So from here on out, we're going to be solving rational equations, problems involving equal signs. So for all of the problems in Chapter 5, Section 4, we're going to be solving rational equations, and we will follow these steps on the first page of this worksheet. Here we notice that we have a rational equation because we have fractions and we have an equal sign in our problem. So we're going to follow those steps on the first page of this worksheet. For step 1, we're going to factor each denominator if possible and find the LCD. The implied denominator here is just a 1. Here our denominator is p and here our denominator is 4. None of these denominators can be factored, so I've just put a check mark here since we've checked but nothing can be factored. And now we can move on to finding the LCD. Again, we can use the trick that we learned in Chapter 5, Section 2 for finding the LCD. First step, copy down the first denominator exactly as it appears. The implied denominator here is just a 1. When your denominator is a 1, you can skip it when you're determining the LCD. So let's move on to this denominator. We'll copy this denominator down, p. Then we look at our next denominator and we ask ourselves, is the factor 4 currently in our LCD? It is not. So we have to add the factor 4, which would give us 4 times p, or 4p for our LCD. For step 2, we find the domain. And to do that, we're going to find the values of p that make the denominator 0. Here, the denominator is an implied 1. There is no variable in this denominator, so this denominator will never be 0. Here, what would p have to equal in order for this denominator to be 0? Well, that would be 0. So we want to say, for our domain, p cannot equal 0 because then this denominator would be 0. Here, there is no variable in the denominator, so this denominator will never be 0. So if we want to write our domain using formal set builder notation, that would look like this. And I'm going to highlight this because we have to remember to check our final answer. If for our final answer we get p equals 0, we have to reject that final answer because p is not allowed to equal 0 because that gives us 0 in our denominator. For step number 3, when you're solving a rational equation, we're going to multiply each term by the LCD over 1. So the fractions will completely disappear and our equation will be much easier to solve. Remember, a term will be a quantity separated by a plus or minus sign that appears outside of parentheses like we see here, or an equal sign. So this minus sign and this equal sign divides our problem into 3 terms. One term, the second term, and the third term. We're going to multiply each of those terms by the LCD over 1. I'll start by taking the 3p and multiplying it by the LCD over 1. The LCD is 4p, so that would be 4p over 1. Then we'll bring down the minus sign and we'll take the term 3 over p and again multiply it by the LCD over 1. And then we'll copy down this equal sign and then we'll take the 7/4 and multiply it by the LCD over 1. If you prefer to write just the LCD, 4p, instead of writing the LCD over 1, you can, but I always like to write it as the LCD over 1 because that makes it a little bit more straightforward when we're doing the canceling. Notice we multiplied this side of the equation by 4p over 1 and this side of the equation by 4p over 1, so we're maintaining equality. Now let's do the canceling. If it helps, we could write this as 3p over 1. And we see there's nothing to cancel since we only have 1 in the denominator. So to multiply this out, 3p times 4p will give us 12p squared, and we just have 1 in the denominator, so we don't need to write it. Here we have a p in the denominator and a p in the numerator, so we can cancel those p's, and that will leave us with negative 3 times 4 to give us negative 12 in the numerator, and just 1 in the denominator, so we don't have to write it. Then we'll bring down the equal sign, and here we have a 4 in the denominator and a 4 in the numerator, so we can cancel, and that leaves us with 7p over 1, which we can just write as 7p. After multiplying each term by the LCD over 1, we've gotten rid of our fractions. Now we need to solve this equation. Notice this equation has a squared term, so we call this a quadratic equation. How do we solve a quadratic equation? We learned how to solve quadratic equations in Chapter 4, Section 8. To solve a quadratic equation, the first step is to write it in standard form. That means we want to have 0 on the right. So to get it in standard form, let's subtract 7p from the right, and then we'll subtract 7p from the left. That will leave us with 12p squared. Then we want to put the minus 7p in the middle, and the constant negative 12 last, and that will be equal to 0 since everything cancels out on the right. Now we have it in standard form. Now in Chapter 4, Section 8, we learned how to solve quadratic equations in standard form by factoring. So we're going to factor, and then we'll set each factor equal to 0. So to factor this, first we need to check for a greatest common factor. There is no greatest common factor. So the next step, we need to find two numbers that multiply to give us the product of these two, negative 144. And those same two numbers have to add to give us this middle coefficient, negative 7. Now you might be able to find those two numbers mentally, but if you're having any trouble finding the two numbers that work, off to the side, I'm going to list all of the numbers that multiply to give us 144. Now we want our numbers to ultimately multiply to give us negative 144, but I'm going to start by just listing the numbers that multiply to give us positive 144. So I think I've got them all here. Now keep in mind, since we actually want our numbers to multiply to give us negative 144, one of these numbers in each pair will have to be positive and the other will have to be negative. So within each pair, if one of the numbers is positive and the other is negative, which of these pairs not only multiplies to give us negative 144, but also adds to give us a negative 7? That would be 9 and negative 16. Now, there are several different approaches you can use to proceed to factor this. I'm going to show you my favorite approach, but if you have a different approach that you prefer, feel free to use that here. The approach that I use, once you find these two numbers, is to draw our two sets of parentheses and make sure to include the equal 0. Since this is a 12p squared, we're going to put a 12p here and a 12p here. If this were an 8p squared, we'd put an 8p and an 8p. If this were a 7p squared, we'd put a 7p and a 7p, and so on. Then we insert these two pink numbers in the blanks. So we'll put a positive 9 in one blank and a negative 16 in the other. We have to now examine each parenthesis and divide by that parenthesis GCF. The GCF between 12p and 9 is 3, so we're going to divide by 3. And the GCF between 12p and 16 is 4, so we're going to divide by 4. Let's see, if we divide each term here by 3, that will give us 4p plus 3. And if we divide each term here by 4, that will give us 3p minus 4. And then we'll bring down our equal 0. Again, you might have used a different approach than I did here, and that's okay, but you should end up with this exact same factored form. Once you've factored, then we set each factor equal to 0. So let's set this factor, 4p plus 3, equal to 0, and we'll set this factor, 3p minus 4, equal to 0. Now I'm going to proceed to solve these two equations to get our final answer. Now, before we write down our final answer, we need to remember step 4. For step 4, we need to reject any extraneous solutions. In other words, make sure that our solutions are not one of the forbidden values of p. P cannot equal 0, but 0 was not either of our solutions. So it looks like both of our solutions are valid. So you can write your final answer like this, or if we write our final answer using solution set notation, it would look like this. How could you check your answer? Well, start by taking this first solution, -3/4, and you might want to use your calculator, but you could plug in -3/4 for P here and here and compute this and make sure that it's equal to 7/4. Then you could plug 4/3 in for P, compute this, and make sure that again you get 7/4. Let's take a look at another example. Here we see that we have a rational equation. So whenever you're solving a rational equation, you can follow the steps on page 1 of this worksheet. Step 1, factor each denominator and find the LCD. So to start, we want to factor this first denominator. We learned how to factor in chapter 4, so I'm going to factor very quickly for this example, but if you need extra practice factoring, please review my chapter 4.5 video. I'll start by copying down the numerator, and this denominator can be factored as n plus 3 times n minus 1. Then we'll bring down the minus sign, copy down the numerator. This denominator can be factored as n plus 2 times n minus 1, and we'll bring down the equal sign, again copy down the numerator, and this denominator can be factored as n plus 3 times n plus 2. Once you've factored each denominator, then we want to find the LCD. Each denominator must appear in our LCD. Start by copying down the first denominator exactly as it appears. That leaves us with n plus 3 times n minus 1. Then look at the next denominator and add the missing factors to your LCD. Let's see, does the factor n plus 2 appear in our LCD? No, so we need to add it. Does the factor n minus 1 appear in our LCD? Yes, so we don't need to add it. Then let's examine the third denominator. Each factor in this denominator must appear in our LCD. Does the factor n plus 3 appear in our LCD? Yes, so we don't need to add it. Does the factor n plus 2 appear in our LCD? Yes, it does already, so we don't need to add it. So this is our LCD. For step 2, we find the domain, and to do that, we find the values of n that make each denominator 0. Now, once you've factored, you want to look at the factored form for the rest of the problem. So don't look at the original form anymore. Completely ignore it. We're going to rely on the factored form for the rest of the problem. So let's figure out what values of n make each denominator equal to 0. Let's start by copying down this first denominator. And we want to know when is this denominator equal to 0. Then let's copy down this next denominator right here. And we want to know when is this denominator equal to 0. Then let's copy this denominator right here, and we want to know when is this denominator equal to 0. Remember, when you've got a factored quantity equal to 0, to solve it, you just need to set each factor equal to 0. So we'll set n plus 3 equal to 0 and n minus 1 equal to 0. If we solve that, that will leave us with n is equal to -3 and n is equal to 1. Now remember, this denominator cannot equal 0. That's forbidden, so I'm going to put slashes through each of these equal signs. Then to solve this, we can again set each factor equal to 0, and if we solve that, we will get n equals -2 and n equals 1, but again, the denominator cannot equal 0, so these are our forbidden values, so I'm going to add slashes through the equal signs. Same thing here. To solve this, we just need to set each factor equal to 0, and if we solve that, we will get n equals -3 and n equals -2, and again I've added slashes through all of these equal signs. Now let's write our domain using set builder notation. So here's our set builder outline, and let's write all of the forbidden n values. Let's see, n cannot equal -3, and we don't have to write this in order from least to greatest, but I'm going to do so. So let's see. Then we can write n cannot equal -2. And then let's see, we can say that n cannot equal 1. And everything else is just a repeat of what we've already said. We already said that n can't equal 1, that n can't equal -3, and that n cannot equal -2. So we don't need to repeat that. Now, I wrote this all out this first time so that you can see the mental process we go through when we're finding the domain. But most people don't write down this whole process. Most people find the domain mentally when possible. And to do that, you just have to look at the factored form of each denominator and examine each factor and ask yourself, what do you have to plug in for n to make that factor 0? Let's see, if n was -3, we'd have -3 plus 3, which would give us 0. So n can't equal -3. Here, n can't equal 1 because then we would have 1 minus 1, which would give us 0. Here, n can't equal -2 because then we'd have -2 plus 2, which would give us 0. So instead of going through this whole process, you can find the domain by just mentally examining each factor and figuring out when that factor would be 0. So I've highlighted this domain because we're going to come back to it in the last step. For step 3, we're going to multiply each term of the equation by the LCD over 1, and the fractions will disappear. So again, we're not looking at the original problem anymore. We're always looking at this factored form. Again, a term is a quantity being separated by an addition or subtraction sign outside of parentheses or an equal sign. So we have 1, 2, 3 terms. We're going to multiply each of those terms by the LCD over 1. I'm going to start by copying down this first term right here, and I'm going to multiply it by this LCD over 1. So I've multiplied it by n plus 3 times n minus 1 times n plus 2 over 1. Then let's copy down this subtraction symbol, and then we'll take this second term and write it here. And again, we're going to multiply by the LCD over 1, and then we'll bring down the equal sign, and we'll take this term and write it right here, and we're going to multiply it again by the LCD over 1, as I've written right here. Now, our equation momentarily looks much more complicated, but as soon as we cancel, we'll see that all of the fractions disappear. Let's see. We can cancel the n plus 3 that appears in both the numerator and the denominator, and here we can cancel the n minus 1 that appears in both the numerator and the denominator. That leaves us with 5 times n plus 2 in the numerator. And since we're only left with 1 in the denominator, we don't need to write it. Then let's bring down the subtraction symbol. And here we can cancel the n plus 2 that appears in both the numerator and denominator, and the n minus 1 as well. That will leave us with 3 times n plus 3 over 1. Then we'll bring down the equal sign, and then we can cancel the n plus 3, and we can cancel the n plus 2. That will leave us with 1 times n minus 1, again, all over 1. Now our equation is much simpler and easier to solve. Now we just need to solve. And to solve, let's start by distributing. If we distribute the 5, that will give us 5n plus 10. And then if we distribute the -3, that will give us -3n. And make sure to include this negative when you're distributing. So -3 times 3 will give us a -9. And then if we distribute the 1, that would just give us n minus 1. Now let's combine like terms on the left side here. 5n minus 3n will give us 2n, and 10 minus 9 will give us a positive 1. And there's nothing we can simplify on the right at this point, so I'll just carry down the n minus 1. Now we want to proceed to solve. This is just a basic linear equation. It's not a quadratic equation like we saw in the previous example, since there is not an n squared term. So to solve this basic linear equation, we want to get n to appear on only one side of the equal sign. So I'm going to subtract n from both sides. 2n minus 1n will just give us 1n, or n, plus 1. And on the right side, we have minus 1. And now to isolate n, I'm going to subtract 1 from both sides. And that will leave us with n is equal to -2. Now be very careful, because after all this hard and correct work, if you write this for your final answer, you'll be wrong, because we always have to remember step 4. We have to reject extraneous solutions. Unfortunately, sometimes when we're solving rational equations, we can get solutions that aren't valid because our solutions would give us 0 in the denominator. So for step number 4, we look back at our domain, and if our solution is any one of the forbidden values, we have to reject our solution. Our solution is -2, and that value is forbidden, because if n is -2, that would make this denominator 0 and also this denominator 0. So since this is one of the forbidden values, we have to reject it. And since we rejected our only solution, that means that the final answer is no solution. That means that there is no value that you could plug in for n that would make this side of the equation equal to this side. Let's try one last problem together. Here again, we see an equal sign, so we know that we're dealing with a rational equation. And to solve rational equations, step one, we're going to factor each denominator if possible and find the LCD. This denominator here cannot be factored, and this denominator here also cannot be factored. But let's see if we can factor this denominator here. To factor this denominator, we need to find two numbers that multiply to give us negative 12, and those same two numbers have to add to give us 1. It looks like 4 and negative 3 would work because 4 times negative 3 equals negative 12, and 4 plus negative 3 equals 1. So you can see I've just copied this exact problem right here. The only thing that I've changed is I've written this denominator in factored form. Now that we've factored any denominator that could be factored, which was just this denominator here, next we want to determine the LCD. Remember, each denominator must appear in our LCD. Let's use our trick to find the LCD. We'll start by copying down this first denominator, x plus 4, and then we'll examine the other denominators and add in any missing factors. Let's see. The factor x minus 3 is missing from our LCD, so let's go ahead and add that factor. And then let's examine the last denominator. Is the factor x plus 4 in our LCD? Yes, it is, so we don't need to add it. Is the factor x minus 3 in our LCD? Yes, it is, so we don't need to add it. For step number 2, we find the domain. And to do that, we need to find the values of x that make each denominator 0. Now, instead of writing out all the steps like I did in the last problem, let's just do this together mentally. So here is my set builder outline. Then let's ask ourselves, what value of x would make this denominator 0? That would be negative 4, because negative 4 plus 4 would give us 0. So x cannot equal negative 4 because that would make this denominator 0. Next, let's ask ourselves what value of x would make this denominator 0, and that would be 3 because 3 minus 3 would give us 0. So x cannot equal 3 because that would make this denominator 0. Next, let's examine this denominator. Looking at the factored form of this denominator here, what values of x would make this denominator 0? Well, if x was negative 4, this factor here would be 0, but we've already stated that x cannot equal negative 4. And let's see, if x was 3, that would make this factor 0, but we've already stated that x cannot equal 3. So it looks like we've established our domain by listing all of the forbidden x values. And again, I've highlighted this because if for our final solution we get either of these two forbidden x values, then we'll have to reject that solution. Step 3, we're going to multiply each term by the LCD over 1, and that will make our fractions disappear. Again, we're focusing on the problem in factored form, not this original form of the problem. So let's see, we have 3 terms here, 1, 2, 3, and we're going to multiply each of those 3 terms by the LCD over 1. I'm going to start by copying down this term right here, and I'm going to add parentheses around the numerator and the denominator, since both the numerator and the denominator are made up of more than one term. And then I'm going to multiply by the LCD over 1. Next, let's copy down this addition sign, and then I'm going to copy this expression right here, and again I'm going to add parentheses around the numerator and the denominator. And then let's go ahead and multiply this term by the LCD over 1, and then let's copy down this equal sign, and we'll copy this term right here. And if you'd like, we can add parentheses around this numerator. And then let's go ahead and multiply this term by the LCD over 1. Now that we've multiplied each term by the LCD over 1, we can cancel and our fractions will disappear. Here, we can cancel the x plus 4 that appears in the numerator and the denominator, and that will leave us with x plus 1 times x minus 3. And we're left with 1 in the denominator, so we don't need to write the denominator. Then, if we examine this expression here, we can cancel the x minus 3 in the denominator and the numerator, and we'll bring down the plus, and that will leave us with x plus 1 times x plus 4 all over 1. Then let's bring down this equal sign, and if we look at this expression here, it looks like we can cancel the x plus 4, and we can also cancel the x minus 3. That will leave us with this expression here, x squared plus x plus 16, and we have 1 in our denominator, so we don't need to write it. Now that we've gotten rid of our fractions, next we want to solve this equation. Now notice, this equation is a quadratic equation since we have an x squared term. Remember, in Chapter 4, Section 8, we learned to solve quadratic equations by first writing in standard form. So let's go ahead and write this equation in standard form. To do that, let's go ahead and FOIL this expression here. X times x will give us x squared. X times -3 will give us -3x. 1 times x will give us a positive 1x, or just x, and 1 times -3 will give us -3. So here we FOILed this expression here. Then let's bring down the plus sign, and let's go ahead and FOIL this expression here. X times x will give us x squared. X times 4 will give us a positive 4x. 1 times x will give us a positive 1x, and 1 times 4 will give us a positive 4. So here we FOILed this expression. And for now, let's just bring down this equal sign and this expression here. Now, we want to get this in standard form. So let's start by working on this left side here and combining like terms. 1x squared plus 1x squared will give us 2x squared. -3x plus 1x plus 4x plus 1x will give us a positive 3x. And -3 plus 4 will give us a positive 1. And let's again bring down the equal sign, and we'll just carry down this expression here. Now, to write this in standard form, we want to get 0 on the right. So I'm going to subtract the x squared, and then I'm going to subtract the x, and I'm going to also subtract the 16. Now we've subtracted away everything on the right, and that will leave us with 0 on the right. On the left, 2x squared minus 1x squared will leave us with x squared. 3x minus 1x will give us a positive 2x. And 1 minus 16 will give us -15. So now we've written our equation in standard form. So I've added these instructions here. To solve a quadratic equation, we first write in standard form, which is exactly what we did here. Once you've written your quadratic equation in standard form, next we will factor, and then we'll set each factor equal to 0. To factor this expression, we need to find two numbers that multiply to give us -15 and to add to give us 2. Those two numbers would be 5 and -3. So we'll factor this as x plus 5 times x minus 3, and then we'll bring down our equal 0. Now that we've factored, we set each factor equal to 0. So we can set this first factor equal to 0, and then we can set this second factor equal to 0. And if we solve this equation, we'll get that x is equal to -5. And if we solve this equation, we'll get that x is equal to 3. Now, before we write our final answer, we need to remember step 4, where we reject any extraneous solutions. So we need to look back at step number 2, where we listed the forbidden x values. And we'll check both of our solutions to make sure that they're not forbidden. X equals -5 was not one of the forbidden x values, so this is a valid solution. X equals 3 was a forbidden x value, so this is not a valid solution. We need to cross it out. X equals 3 can't be a solution because that would give us 0 in our denominator, resulting in an undefined value. So since we rejected this solution, our final answer is only this solution, x equals -5. Or we can write our answer using solution set notation, which would look like this. So if we plug in -5 for x, it makes this side of the equation equal to this side of the equation. 3 was not a valid solution because if you plug it in for x, it doesn't make the two sides of the equation equal. The result is just an undefined value.